Okay, welcome everyone. Oops, we're getting feedback. Hang on. Okay, welcome everyone to Astronomy State of the Art. This is one of our periodic live sessions. We try to hold them every 2 or 3 weeks, and we'll continue that. We'll try and move the time slot around a little bit, although some people like this time slot. I know everyone's dispersed geographically. So everything's on the table for these sessions. Questions about any topic in astronomy, though I can't guarantee I can answer absolutely everything. Floor is open.
All right, so the first question is from Alice Amanda, and she asks, can you tell me a little bit about ALMA? I have read that it has been used to search for monster stars in dark clouds.
ALMA is the Atacama Large Millimeter Array, and it's probably the preeminent new radio facility in astronomy. People have been anticipating this for a number of years. So the background is that radio astronomy has been able to use the technique of interferometry for decades, where you take the information from separate radio telescopes and combine it as if you had a single radio telescope of the size of the largest separation between the telescopes. So combining information from multiple telescopes obviously increases the effective collecting area, but more dramatically it increases the resolution. Because if you remember, whether it's an optical, infrared, X-ray, or radio telescope, the resolution scales with the aperture. And if you're limited just to the size of a radio dish, and they're usually 10, 15, 20 meters across, that determines your radio resolution. But if you can coherently combine the radio information from separate radio telescopes, that's done using waveguide technology, you can pretend like you have a telescope that's hundreds of meters across, or even a kilometer, by the technique of interferometry. That technique is very mature when used at centimeter wavelengths, and the Very Large Array, which many of you have heard of and you can see if you drive through the San Agustin Plain in New Mexico, beautiful part of the country, just if you're touring anyway, it's worth visiting, is a set of radio telescopes that have been used this way for decades. Doing this trick at millimeter wavelengths, 10 times shorter wavelengths than centimeter wavelengths, is harder, because maintaining the coherence of the radio waves when they're much shorter is technically more challenging. And the second problem, when you go to the shorter wavelengths, the millimeter regime, is that the atmosphere is no longer completely transparent. The air has substantial absorption from molecules of mostly water vapor and other ingredients in the atmosphere, and so you don't see as well at millimeter wavelengths through the Earth's atmosphere. So ALMA is the preeminent attempt to circumvent both of these problems. It's the first set of radio telescopes designed to work at millimeter wavelengths and work as an interferometer. I forget the exact number of dishes. I think it's 18 to 24 in that range. They're not all fully operational. And then the second ingredient of ALMA is its location. It's in the northern part of the Atacama Desert in Chile. It's at an altitude, it's on the Chalendor Plateau, extremely dry part of the world. There are places nearby where it hasn't rained in a century, literally. And the altitude is 5,200 meters. And that is really a difficult altitude to work at, but you're above a good fraction of the Earth's water vapor. So this is the best millimeter radio facility in the world. It's starting to do its work, and to get back to Alice Amanda's question, the main scientific areas where ALMA contributes are in the area of star formation, and also in the area of looking at very distant galaxies, and also looking at cold material in the universe, which emits lines based on molecular transitions. So the monster star research is just one example of the kind of things that ALMA can do. It's able to drill down or see through dense regions of gas and dust where optical telescopes simply can't see anything, and reveal the places where massive stars are forming. There's a little informal competition amongst astronomers to find the most massive star. The record holders are around 140 or 150 times the mass of the Sun. Some have claimed even 200 times the mass of the Sun. And ALMA is working in that area too, trying to find these incredibly massive stars, which are in very chaotic regions full of gas and dust, where only a radio telescope, and actually a millimeter telescope, can really work well.
All right, the next question is from Julian. So there is a new nova in Delphini, which I've seen. Both nova and type 1a supernova come from white dwarfs. So what are the different conditions that make one explode and the other just flare up?
Good question. Nova and supernova, the relationship of the word sort of gives you an indication that a supernova is an extreme form of a nova. Nova, of course, the word comes from the Latin for new, and so these were seen by ancient people as being new stars in the sky, because what they were seeing was a star that was typically just below the limit of the naked eye, which by a flaring event came to be visible to the naked eye, and so to a naked eye observer, it just looked like there's a brand new star in the sky. And then some period of time later, weeks or months, it would disappear again. So that's the origin of the word nova. And the phenomenon, of course, has been known since well before the telescope, because supernovae have been observed for millennia and novae have been observed for millennia before people understood what was going on. There's actually no single phenomena responsible for either novae or supernovae. They're multifaceted because there are a number of things that can cause a star to flare. And there are a number of things that can cause a star to explode or detonate and end its life. And that's the fundamental distinction. A nova is a recurring event. It's not strictly periodic, although there are a few novae that are periodic. Most of them occur on an irregular time scale that could be from years to decades to even centuries. You have an episodic flaring of a normal star, usually a massive star. A supernova is a cataclysmic event that represents the end of a star's life. So typically the difference is, for example, in a binary system where a star is having material fed onto it by gravity from a close companion, that material, as it's fed onto the star, will be compressed by the gravity of the star, will ignite fusion, so the infalling material is triggered into nuclear fusion by compression and gravity, reaching a temperature of, say, 10 million Kelvin, and that causes a flaring of that star because it suddenly has a new source of energy beyond whatever was going on inside the star. And because that siphoning of gas is episodic and not even completely regular, that will be seen as a nova in the sky, a star that just, where you can't necessarily see the two stars and resolve them on the sky, where it seems like one star is for much of the time not doing much of anything, and then suddenly it flares up, by which I mean it could brighten by a factor of 10 or even factor of hundreds or thousands. A supernova can have the same thing going on, where a dwarf star, white dwarf, has material added from a companion just by gravity interactions in a binary system. But in the case of a supernova, it leads to a cataclysmic and final event. When the white dwarf passes what's called the Chandrasekhar limit, named after a famous astrophysicist of the last century, it reaches the point of final detonation as an explosive ending to the star, and nothing is left after that except a black hole or a neutron star. So novae recur. They're less dramatic, they're less luminous, and their episodic behavior has been known for centuries. Supernovae are much more dramatic. That dying star could rival the light of an entire galaxy. That's the end point, so there's no recurrence of that phenomenon. What's left behind is a dark remnant.
The next question is from Stanley. The age estimate of the universe has changed gradually over the years, with Stewart Observatory having a number posted to great accuracy. Is there a protocol for changing this number and making it the new standard? Or do astronomers keep their own number that they are comfortable with?
Yeah, that's a very good question because it alludes to the culture of astronomy and how we declare numbers and then get everyone to agree on them. The age of the universe is one of the numbers that people don't necessarily all agree on because different research groups are approaching that measurement in different ways and they're getting different answers. In the larger terms, the International Astronomical Union is the arbiter of astronomical data or numbers. That's the international consensus astronomers would reach, where they agree on definitions and names and some measurements. And so the IAU, as to use its acronym, is the outfit that gives the names to things. Allows objects in the solar system to be named a particular way, or craters on the moon or Mars. The IAU has tended not to step too hard into being the arbiter of numbers in astronomy. However, there is an approved number, for example, for the distance from the sun to the center of our galaxy. It's about 27,000 light years. The exact number is maintained on an IAU website, and it represents a consensus of the astronomical community. The IAU doesn't actually quote or support, if you like, one number for the age of the universe, in part because the history of this measurement has taken the number over a very large range. You may, an interesting little historical note in astronomy is that because Hubble was slightly misled in his measurements of the distances to galaxy, it turns out that there are two different kinds of Cepheid variables. That was the tool he used to show that Andromeda and other nebulae were distant systems of stars. Hubble actually got the distance scale, the distance to galaxies, very badly wrong by a factor of 6 or so, and that led him, in the Hubble expansion, where you trace back the expansion to infer an age of the universe, to grossly underestimate the age of the universe. He actually published a number that was something like 2.5 billion years. That was a problem, so there was a time, way back, almost a century ago, when the age of the universe seemed to be too small, because we already had a pretty good idea that the Earth was older than 2.5 billion years. So that's a sign of how difficult it's been to measure the age of the universe. Things got a little better in the 70s and 60s with big new telescopes, but even through the late 70s and into the 80s, there were essentially two camps of astronomers who, based on different measurements of the Hubble expansion, were defending quite different ages for the universe. One number essentially 13 or 14 billion years, and the other quite a lot shorter, like 7 or 8 billion years. And there was no agreement between them. Their measurements didn't even overlap in terms of the error bars. Quite a big problem in astronomy. That debate gradually resolved with the Hubble Space Telescope measuring the distance scale, one of the important things Hubble did in its first 6 years in orbit. And now we've measured the local expansion rate fairly accurately. The local expansion rate, coupled with the measurement of how much mass there is in the universe, gives you a time you can trace back to the Big Bang. And so we've known for perhaps a decade that that number is around 13 billion years. The crystallization of that number to the level you read about now, where it's quoted to that extra decimal place, and where, if you notice, it's changed from 13.7 billion to 13.8 billion just in the last year or so, is based on microwave background observations. These are very clever measurements of the characteristic size of fluctuations in the early universe measured with microwaves that essentially give us a meter stick to measure the early universe, which we then compare to phenomena in the more recent universe, and that gives us an age measurement. So these latest measurements are actually accurate to that decimal place, to essentially 100 million years out of 13 billion. And that's the level at which astronomers are now arguing. But they're still looking at systematic errors and other problems, so the IAU has not weighed in on this debate and supported one number versus another, but it's pretty unlikely we're wrong by more than 5 or 10% now. The age of the universe is extremely well measured, and it's in the high 13+ billion year regime.
Here's a question from Alice Amanda. I have read that the black hole in NGC 3783 is pushing away cold dust above and below the black hole by a weak radiation from the hot component of the dust torus. Is this the only black hole so far to have done this?
So this is an interesting research area. I'll give a little background before answering the question. Black holes exist in the centers of all galaxies. That's a research result of the last few decades. Hubble Space Telescope did a lot of this work, but ground-based telescopes too. But it appears that most of these black holes are not in a highly active state. They're quite dark or quiescent. They're not emitting a lot of radiation or energy. And our galaxy is a good example. 4 million solar mass black hole is not doing too much of anything. The galaxy Alice Amanda alluded to is a fairly nearby galaxy where we can study it in quite good detail. And now people have made a whole research field out of the interplay between the center of a galaxy and the black hole that it harbors. So what we really want to know, a big question, is given that the center of the galaxy is basically a big old pileup of stars and there's lots of gas and dust and plenty of gravity to bring it towards the center, why are black holes so quiescent? Why are so few black holes booming with radiation? Well, first of all, as a side step, why should they be booming? Well, if there's a lot of fuel, even though the black hole itself is black, the material falling into the black hole will be accelerated by gravitational energy, essentially, and that accelerating material will radiate enormous amounts of energy. So we expect the vicinity of a black hole to be very bright indeed if there's lots of stuff there. The result that Alice Amanda is referring to for this one NGC galaxy has been seen around other galaxies too. What we see is that there can be outflow from the black hole, and that outflow affects the material in the environment. And essentially the outflow can keep away the stuff that would otherwise fuel the black hole, thereby quenching its activity. So we think what goes on in black holes is a sort of cycle of activity. It's not regular or like a metronome or like a clock. It's not a periodic process by any means, but an episodic behavior where for most of the time the galaxy is fairly quiet and the black hole is starved. And that starved probably because a prior episode of activity essentially cleared out all the material that it might otherwise eat. And with this galaxy, we're seeing that actual process happening. We're seeing outflow from the vicinity of the black hole, clearing out a region or pushing away gas and dust. And for some period of time after that, the center of the galaxy will be empty enough of fuel for the black hole that we would expect that black hole to essentially go dark for some period of time. But the big question is, what is the duty cycle, as it's called, of this activity? In other words, what fraction of time is a black hole on and what fraction is it off? We don't really know. The best estimates of the duty cycle are around 1% or a bit less. So black holes only spend about 1% of their time active and 99% of the time inactive. The physics of how that happens is very complicated and is the subject not just of astronomy observations, but also big computer simulations. It's a very exciting and active area of astrophysics.
The next question is from Stanley. The Stewart Mirror Lab seems to have lots of mirrors in various stages of manufacture. Are they really getting that good at the process, and will it lead to an expansion of the facility?
I'm glad you asked that question because we've just had a major success just this last weekend. I didn't want to just come out here in a live session and toot our horn, but just this past weekend we cast a third 8.4 meter mirror for our Giant Magellan Telescope to be situated in Chile, and that casting, as far as we can tell, was a success. What happened last weekend was the phase where the borosilicate has been added on top of the molds. I mean, the details of how this works are in the module in the course, of course, on telescopes, because I show a lot of information about this. But basically, last weekend, the borosilicate was melted, the oven was taken through a temperature cycle up to 1160 C, was cooled down and stopped spinning. And, of course, then you actually have to wait a couple of months before you can crack the lid and see whether you've got a good mirror. But the cameras inside indicate that everything in the critical phase of the heating and melting worked fine. And there were a lot of dignitaries there. We have major partners on this telescope, which is going to cost close to $1 billion. So we had the presidents of major universities and foundations and organizations that are partners. So it was a pretty high-stakes event. The pressure on the Mirror Lab for that would have been phenomenal. I mean, it's hard enough to do these mirror castings without having all the deep-pocketed donors there watching and wondering if you're going to screw up. Well, nobody screwed up. Everything went fine. And where we are in that project is that we've made the central element of the Giant Magellan Telescope. And then in addition to the central element, there are 6 petals, if you like, or just mirrors, off-axis paraboloids that will go around it. And now we've made the second of those petals, and the third will come, and the fourth and fifth and sixth. With 4 out of the 7 mirrors, we can get a first light going for this telescope. We don't actually need all 7 mirrors to launch the telescope. There will be placeholder blanks for 3 of the petals, and we'll start doing science late in this decade. But to answer the general question about the Mirror Lab has been phenomenally successful. They've worked their way up over 20 years, essentially, from 1.3 meter to 2 meter to 4 to 6.5 and now 8.4. And the oven can only make a mirror of that size. 8.4 is the biggest it can make. And now we've made 5 of those, actually, 3 for the GM2 and 2 for another project. And so I would say the Mirror Lab is phenomenally successful. As for the part of the question of Can we do more or faster or expand? That's really hard. The only way we could do better or make more mirrors or make them quicker would be to double up and have a second oven so that we could be polishing one mirror while we're casting another. But at the moment, and we'd have to double the staff. But essentially, these expertise of these people is very specialized, and it's the same set of people that know how to create the mirrors and then polish them. And so that set of people just moves from polishing to casting, back to polishing, back to casting, and we have to do that cycle. To double up and expand the facility would cost us probably $50 or $60 million that we don't have. So unfortunately, the Mirror Lab is working flat out, and they're sort of going as fast as they can, which essentially means one complete and polished mirror every 18 months.
All right, so let's quickly just go back to the supernova questions, and as a follow-up on that. What distance away would result in a serious effect of a supernova on Earth? Are we aware of any potential future events in our neighborhood, much like we are waiting for Betelgeuse to eventually nova?
Right, good question. The level of proximity where a supernova is life-threatening or biosphere-threatening is a matter of a little debate, but we do know for the supernovae that occur in binary systems, their luminosity or their brightness, number of watts they emit, is a very well-regulated number. It's known to within 15%. So there we're very certain. We can predict the effects at any particular distance. There's basically two zones. There's a zone around from, say, 50 light years away to about 30 light years away, where a supernova going off would cause a significant impact on the biosphere. It would do so by altering the ozone content, so the high-energy radiation. It's not just high-energy radiation, but also neutrinos come out of supernovae, and cosmic rays are created or accelerated by supernovae. So there's high-energy photons and high-energy particles of various kinds, and they each have their own effects. The main effect of a supernova at that distance would be to increase the mutation rate on the Earth, on the surface-dwelling organisms. Creatures in the sea wouldn't notice this. And also to affect the ozone layer in a bad sense, because the ozone layer is a very important protective component of the atmosphere, keeping us safe from ultraviolet radiation in particular. So the twin effects there would be to cause a surge by perhaps an order of magnitude or maybe more in the mutation rate of all organisms on the surface, including us. Is that going to be a devastating effect? Probably not, but it's very hard to tell. I mean, it could spike cancer rates and cause some more serious problems we can't anticipate. It's very hard to model what the effect of that would be. So that would be a deep concern. Loss of, or contamination, or degradation of the ozone layer is a really big problem for the Earth. Closer than about 15 or 10 light years, then we have a much more serious problem. Then we actually have destructive effects from the radiation and the particles themselves. I mean, these impacts, these high-energy particles or cosmic ray impacts into tissue and cells will actually cause problems. And at that point, you can potentially just kill organisms. They're sort of being blasted by radiation, essentially, in a slightly diluted version of what happens near a nuclear explosion. So for a very close supernova, the effects are much more profound, much more dramatic, and probably life-ending for many organisms on the surface. And also, you'd have a very big disruption of the Earth's protective blanket. I mean, not a level where it could recover. So that's a threat to the biosphere. What are the possibilities? We do have a pretty good stellar census within, say, 30 light years. We don't know every star, but we certainly know all the massive stars that are able to die as a supernova. We don't have to worry about the low-mass stars like the Sun, because the Sun and stars less massive than the Sun won't die that way. And so we pretty much know where the few dozen stars that are massive and late in their lives are in the sky, and we can basically try and look at them as carefully as possible and say how far they are from their death phase. And that's sort of where it sits, unfortunately, because if you were to ask, based on astronomy observations of a particular massive star, say one that you know has moved into its late stages of fusion, where it's fusing silicon into iron and reaching really towards the end of its life, or starting to advance those nuclear stages that happen in a crescendo at the end of a massive star's life, our observations are not precise enough to age date a star from its point of death. They're just not that precise. Because remember, these are stars whose total lifetimes may be 10 million years, and you're asking how well you can diagnose whether they're in the crescendo of the last part of their lives that lasts a century or so, or a decade. You know, is this star a decade away from blowing? That's the question you really want to know the answer to. And the answer is we don't have precise enough measurements. The best precision on our estimate of stellar lifetime is more like millennia than decades, and that's not particularly helpful, because saying a star could go off within the next 1,000 years is not really telling you to do anything about it. The warning we would get if a star were about to go supernova, it's not clear how much warning we would get. And I guess the best news, to leave it on a positive note, is that only one, or depending on who you talk to, two of the stars in the solar neighborhood are both massive enough and close enough to be in that category where they could do beyond a sort of mild impact on the ozone layer, could do something more dramatic. And there's no evidence that either of those stars are in the very end stage of their lives doing fusion, but we simply don't know.
Julian asks, there's been a recent story about a very old star nearby, similar to the age of the universe. As stars don't come with a best before sticker, how do you measure the age of a star?
Yeah, good question. It's actually hard. You need a model. There's nothing, as you implied, Julian, measuring stellar properties is tricky. Really, the only properties we measure directly are the luminosity, assuming we know its distance, so we know how much energy is coming out, and we measure the surface temperature, which is an indirect indicator of what's going on deep inside and what fusion process is occurring. If the star is in a binary system, we also get the mass. So in cases where we have those three pieces of information, we can make pretty good models of how stars live their lives, and those models are robust enough to attach ages to stars. Now, anytime you're talking about a star that's anything like the age of the universe, say more than 10 billion years old, that star is must, of course, be a very low mass star, because only the lowest mass stars live more than 10 billion years. So that star is either going to be a red dwarf or a white dwarf. Any star more massive than that would already have died, and then you'd be talking about a black hole or a neutron star, and we don't know how to measure the ages of those things. So essentially all the oldest stars in the universe are either red dwarfs or white dwarfs, essentially low mass stars or the fading embers of once living stars. And both of those situations are cases where our models are pretty good, and so we can make an age estimate that's probably maybe only accurate to 10%, but that's pretty decent. So when people say they've measured a star that's 13 billion years old, there's an error attached to that, or an uncertainty of about 1 billion years, probably. I don't actually know the particular case you're talking about, but the models are rarely better than 10%. That's very interesting, and if it's found in our own galaxy, since our galaxy evolved by agglomerating, by mergers and acquisitions of smaller galaxies, this is a star that was present right from the beginning of our galaxy. It was present in the original region of space where the pieces of our galaxy started being assembled. So that's really exciting when we do find such an old galaxy in our, an old star in our galaxy. The sun is 4.5 billion years old. Most of the stars around the sun are a few billion years old. It's actually really hard to find stars more than 10 billion years old in the Milky Way, and they tend to be in the halo, which we think formed first. So this galactic archaeology, by using old stars, is really important. And I'm glad you asked the question, too, because it connects beautifully to the question about the age of the universe, where I talked about how that's measured from the expansion rate and the microwave background. The measurement of the age of the oldest star by stellar models is a completely different way to put a constraint on the age of the universe. It just depends on stellar physics. It doesn't depend on Hubble expansion or cosmology or anything. It's pure stellar physics that we understand pretty well. So with the oldest stars you can find in our galaxy, you have the potential to bring down the Big Bang model. You have the potential to refute your measurements from cosmology. And so people are aware of this, and they've spent quite a lot of effort looking for the oldest stars in our galaxy because it's a cross-check on our whole understanding of the age of the universe. And if you found a star that was more than 13.8 billion years old, beyond the error, so 14 or 15, and you had the measurement quite accurate, you'd have made a big problem for our understanding of the universe. So the fact that this old star in the Milky Way is a little less than the age of the universe measured from cosmological and completely different measurements is reassuring. It's actually an affirmation of our Big Bang model, of our understanding of the universe, because the universe clearly can't have any objects in it that are older than the model says the universe's age should be, and that so far has proven to be the case.
Right, another one from Alice Amanda. Can you tell me more about BOSS, the Baryon Oscillation Spectroscopic Survey?
BOSS is an exciting survey. The context for the acronym of this survey is that astronomy has moved in the last decade or so towards extremely efficient spectrographs where you use fibers or slits to measure the spectra of hundreds or in fact thousands of objects at once. Now BOSS takes this to another level by measuring tens of thousands of galaxy redshifts all simultaneously, by having a very large field of view and by sending light through slits to different regions of a spectrograph and then measuring all the spectra at once. Now astronomers spend decades measuring galaxy spectra one at a time, where even if you have a large telescope, that's just very inefficient. So BOSS is a wonderfully efficient way of doing spectroscopy. What is the point of a survey like this? Because we do have redshifts for over 1 million galaxies, probably close to 2 million galaxies now. Why do we need yet more redshifts when we already have so many? When we know the universe is expanding, we've measured the basic features of the nearby universe very well, so why do we need yet more redshifts? The real answer for the BOSS project, although we'll do multiple kinds of science, the big hook for the project is dark energy. What BOSS is designed to do is by measuring, by just industrial scale harvesting of galaxy redshift, it's going to find clusters and the large-scale structure of the universe on large scales and in exquisite detail. And with BOSS has imaging components, so there's direct imaging, and there's also the spectroscopy of these galaxies. And in both aspects, you can learn something about dark energy. I'll just stick to one piece of this because there's a lot of science involved in BOSS. Because dark energy works against gravity, in opposition to gravity, we know that in our cosmology theory, structure forms steadily over time as galaxies are built from pieces, and then those galaxies aggregate into clusters. And that has just proceeded in a steady manner through the history of the universe. It's called hierarchical structure formation. The smallest things form first and then the largest structures. So if you had a model of the universe with just gravity, mostly from dark matter of course, you could predict how fast structures would form on different scales. Not just how many clusters of galaxies you would get, but how long they would take to form and what evolutionary stage they would be in at different redshifts or distances. If into the mix you put dark energy, that dark energy, by acting in opposition to gravity, will slow down the formation of large structures in the universe. Even though we don't know what dark energy is, if it acts the way we think it does to accelerate the cosmic expansion, it must also retard the formation of structures in the universe. And so now you get to what BOSS can do. BOSS will measure with exquisite detail and with incredible statistics the way structures form in the not super distant universe, but the mid-distant universe. You don't have to go to the edge of the universe to do this experiment. And by doing so, and comparing to a model, it's going to tell us something about dark energy. For the first point, it's actually going to say whether the way structures form and how long it takes them to form is consistent with the presence of dark energy. Because at the moment, the only evidence we have for dark energy is the overall accelerating expansion. With this set of observations, we'll get a finer scale view of dark energy doing its thing to slow down cluster formation. That's really exciting. It's a whole new handle on dark energy. And as with all innovations like that, we expect and hope that it's going to tell us something more about dark energy, about which at the moment we know very little. So that's the excitement of BOSS, Big BOSS as it's sometimes called. It's a survey that's going to take probably 4 or 5 years to complete. It's commissioned and starting, so we're not going to really see the answers from BOSS for a couple of years.
Next question is from Stanley, and it is, how much effective science will still be able to be done with Kuiper's failure and very limited ability? How much new information will be able to be gleaned from the data already gathered by the telescope?
Yeah, it's a good question, and it's been a little sad episode for astronomers to face, the loss of Kepler. NASA has essentially declared it unable to do its primary mission now. So two things have happened. NASA has declared the original Kepler mission and goal to be unviable with the current spacecraft, so the data that's been taken is all that we'll get. But NASA has also put out a call to the general astronomy community of potential science that could be done with the satellite. The problem with the current situation is because Kepler can't point very accurately, or track or know where it is on the sky very accurately, and because it's pointed at a very crowded region of space. The goal was to monitor as many stars as possible, so there's 150,000 stars in the Kepler field of view. You can imagine that Kepler not being able to point or know where it is very accurately means you're blurring your vision in that crowded field and really limiting your ability to learn detailed information. So what might be done with Kepler? It's not a useless facility. It's just lost the exquisite precision of pointing that it needed to do its primary science of measuring transits or eclipses. If Kepler were able to point at different regions of sky or do different kind of surveys, then its CCD is still working completely well. Its power is fine. I mean, the major systems on Kepler are still working. It's just its pointing that was impacted by the loss of these wheels, reaction wheels. So this is an interesting time. The community is going to come up with proposals for NASA for secondary science or missions that Kepler can still do in its current state, and I have no doubt that the ingenuity of my colleagues will come up with some very interesting things. They're unlikely to be related to exoplanets at all. They're almost certainly going to be completely different kinds of science, which is fine. So that's one part of the answer. The second part of the answer is we're going to continue to read about Kepler discoveries for several years. They were shoveling data as fast as they could to keep up with what Kepler was doing when it had its problem a few months ago. And if you see the professional literature, you'll see that the latest data releases early this year were actually only based on less than 2 years worth of data, although Kepler at that moment had been up for over 4 years. So they're behind. I mean, it just takes a long time to process the data with the accuracy needed to find exoplanets. So given that lag, and given the fact that they know this is all they're going to get, they're going to work, this team, it's a very large team, the Kepler team's over 60 people, they're going to be working like crazy to squeeze every drop of juice they can out of that data, and that's going to take a while. So I'm very sure that for 2, 3, maybe even 4 years, we're going to see new exoplanet results coming out of Kepler. And I do think at the end of that process, even though it didn't live as long as everyone hoped, we are going to see an actual statistical measurement of the number of Earths.
Here's a question from Alice Amanda. How many times can a star reverse its magnetic field? I have read that Tau Botus has reversed its magnetic field 5 times since 2007. Is this unusual or common?
Yeah, good question, and a different topic. We haven't talked about this in these sessions. Well, the simple answer is as many times as it likes. The Sun, in a regular and kind of boring main sequence phase of its life, is quite exciting in terms of its magnetic fields. The solar cycle is 22 years long. And so the Sun reorganizes, and flips its magnetic field every decade or so. And it's been doing that for a very long time. Now, we don't have direct evidence that the solar cycle has been the same length. You know, we only tracked it directly since the invention of the telescope and tracking of sunspots. We have indirect evidence that the solar cycle has been going on for hundreds of thousands or millions of years. And stellar models would tell us that because the sun rotates differentially faster around its equator than at the poles, it must take the magnetic field that lives within it, twist it up, and eventually, in a cycle that's pretty well understood in terms of physics, that magnetic field gets tangled and then has to reform with the flipping of the pole. And that's a periodic process for the sun. Now, the star that Alice Amanda asks about is a different star. So it's a more massive and a more variable and chaotic star. And it's changing its magnetic field more rapidly. And that's probably because it's a rapid rotator. Stars do have different levels of angular momentum that emerges naturally out of the way they form and the gas cloud they form from. It's just a natural variation in stellar properties. And so more massive stars do have more angular momentum, and depending on how they form, they could have a lot of angular momentum, and that angular momentum played out into the way a star rotates means that it will be twisting up and destroying and then reforming its magnetic field more rapidly than the sun, in the case alluded to several times in the last 5 or 6 years. So this probably will continue. For that star, it's just in a more active phase, probably has more angular momentum, probably will form and reform its magnetic field more frequently. Now, stars do change their spin rate over time, so the magnetic cycle is not completely fixed for all time, because as stars interact with their environment or as they lose material, their angular momentum will change, and that'll change the rate at which their solar cycle or their star cycle or magnetic field cycle occurs. But we've seen stars out there that have magnetic cycles as rapid as months, and stars that actually may not even change their magnetic fields for centuries at a time, or it's never been observed, basically. So there's quite a large range.
Okay, here's a question from Bill about the Oort cloud. It has been estimated that the Oort cloud is possibly 200,000 AU in distance. Has science been able to prove this, or is it still a theory? It seems that 3.19 light years would be a very vast distance for the sun's gravity to infinite space.
Yeah, it's a good question. The simple answer is that the Oort cloud, the existence and nature of the Oort cloud is still somewhat of a hypothesis with only indirect data to support it. Because if you think of what it's implying, because of Kepler's law, you can think about the extremely elliptical Keplerian orbits of the comets, which says that the comets, that some of which occasionally come into the inner solar system, get their volatile material gets burned off by the sun, they form a tail and we see them. Those comets that come into the inner solar system where we can see them are a tiny fraction of the overall population. Most comets in any part of their orbit don't come into the solar system at all, or within the realm of the planets. They actually just go from a large distance, maybe 50 or 100 astronomical units as the closest to the sun they get, to a very, very large distance, like 50,000 or 100,000. The other thing that's true of those orbits, because they're so elliptical, those objects, those comets, must be spending the vast majority of their time at very large distances, very far from the sun. Those distances like 100,000 AU. So when you take a snapshot of the comet population, 99.999% of them are going to be extremely far from the sun. Of course, extremely cold, hard to see by their reflected light. I mean, it's hard enough to see a comet when it's in the solar system, let alone a comet when it's 100 times the distance of Neptune. So there's no way we could detect these comets with telescopes. They're so far from the sun that there's no solar radiation causing a tail, so they're just inert, icy rocks. Very, very, very far from the sun in terms of compared to other solar system objects. Therefore, it is just supposition that this cloud exists because we can't see them directly. The inference, based on the fraction of comets that we see coming into the solar system, or the inner part of the solar system where we can observe them, is that there are 1 trillion, that's the round number, it's obviously an order of magnitude number, but about 1 trillion comets in the Oort cloud. And the vast, vast majority of them have never been observed. So yeah, it's actually a hypothesis with some pretty good evidence to support it, but we've never observed the Oort cloud. Why is it so big? That's a good question, because this quasi-spherical cloud surrounding the solar system is so much bigger than the orbits of the 8 major planets. The supposition is that that was the original size of the cloud of gas and dust from which the solar system formed. And in its collapse phase, most of the material collapsed by a large factor due to gravity and conserved angular momentum, and so spun up and collapsed along the poles into a disk, and there's a formation scenario for the planets. And the comet cloud was a sort of frozen relic of the very early stage of this initial gas and dust cloud. And that's, of course, why comets are exciting to solar system scientists, because they are real primordial relics. And when they visit us from these outer frigid zones, they're bringing us evidence of the formation epoch of the solar system 4.54 billion years ago. So they're very important objects for that reason.
Julian asks, given all of the Kepler and the other exoplanet data, how unusual is our solar system?
Yeah, people are still worrying a bit about this. I would say they're not worrying about it as much as they were 5 or 6 or 7 years ago. So for a while, it was looking uncomfortable that we were finding these hot Jupiters, we were finding a lot of exoplanets on quite elliptical orbits, more elliptical than those of any orbits in our solar system. We weren't finding Jupiters in their normal locations or Earths in the normal locations. I mean, it just seemed like our solar system wasn't typical. The Copernican principle was under threat. And part of this has just gone away with time and data. If you want to find a Jupiter at a normal Jupiter location, its orbit is 12 years, and to confirm its orbit is twice that, or something like that, so 24 years. And that's about as long. We've barely been doing exoplanet work that long. In fact, we haven't. So we needed a couple of decades of data to be able to find gas giant exoplanets in normal gas giant locations in our solar system, and they are now turning up, so we know they exist. So it was a little dangerous to conclude something was wrong and we were atypical until we had a long baseline of data. As time has gone by, we started to fill in the gaps, and we started to see what I would call more solar system-like architectures. But there's still a lot of oddballs, and the statistics of this are argued about, actually. The conferences on exoplanets have quite vigorous debates about the underlying population of exoplanets and whether our configuration is typical. I think the other ingredient that exoplanets have given us is to tell us that our solar system didn't always look the way it is. We have very good indirect evidence that the planets in the solar system change positions quite a long time after the formation epoch, and that periodically that can happen elsewhere too. So what you see in a mature solar system like ours is not really an indicator of where the planets have always been or what it looked like at other periods of its history. And that's important to understand when you're trying to say whether we're typical or not.
Right. One more question. I think this will need to be our last question.
Okay.
Is from Tom. I have been looking at Arcturus through my telescope quite a lot in the recent months, and he's noticed a remarkable change. It seems to him that Arcturus is flickering much more lately. Does it have a cycle that it goes through, perhaps like a solar cycle?
That's an interesting question. I'd have to know at what level you were seeing it flicker. I mean, it's exciting that you're measuring quantitative changes with a small telescope. There's tons of light to work with for the Arcturus. If you're talking about flickering at a level of less than 1%, that can happen for a number of reasons that are not necessarily connected with something like a solar cycle. Because this outer envelopes of stars, this is quite a massive star too, have a lot of convective motion because there is, there are solar storms, flares, and prominences. Sometimes flickering can be caused by, individual stellar episodes in the outer parts of a star that are sort of uncoupled to some underlying cycle. If the flickering had any periodicity, that would, of course, be very exciting because at that level, you've got the rotation period of Arcturus is understood, although I don't know off the top of my head what it is, but it is known. If you're seeing evidence of periodicity on another time scale, that's actually very exciting. That's a potential discovery. So a star like Arcturus has a lot of chromospheric activity that can lead to flickering if you have really accurate observations, by which I mean, well under % precision. And there's interesting astrophysics in there. So it's exciting that you're doing this work, and I encourage you to keep doing it. And I encourage you to, contact your local astronomers. I'm probably not your most local astronomer to, or to look at the variable star network of observers. I'm a cosmology type person, so I don't work on variable stars, but there are variable star observer associations of amateurs and professionals working together, and they would be very interested in your data, I'm sure. So thank you, everyone, for participating. We'll reconvene and do another one of these in a couple of weeks and announce it well ahead of time on the Udemy website. In the meantime, keep looking up.